and this will be about media streaming in the functional world. So basically we'll be answering the question how to do media streaming in Elixir. And to do that, I'm going to show you a case study of a kind of real-life problem, but not too serious, so that we can have a little bit of fun as well. So our problem for today is a drum. So a drum is cool because it does bam bam when you hit. And it's also problematic because it takes quite a lot of space. We could have like a small drum, but it doesn't do like proper bam bam, so that's not cool. And we can also have a digital drum, but it is quite like an expensive thing as for a drum. So the idea is, let's make a virtual drum. So the concept for that is the following. We will use the camera to track the movement of a user's hand. And we're going to stream that over WebRTC to our backend, to our server. And we're going to use WebRTC because it's adjusted for like low latency streaming, and we are going to need low latency here. Then we're going to use a neural network to detect where the hand is on the stream. And when the user does something like this, then we're going to emit the sound of the drum. And we are going to stream that sound back via WebRTC as well. I told everything, and here is also written. Basically that's it. So for the client side, we're going to use a browser, and that's not the interesting part because everything is built in the browser. So we can use the JS API to get the video and to send it to the server, and then to retrieve the audio from the server and use HTML elements to play it out. However, the server is a bit more interesting, so we're going to receive the video over WebRTC, and then the video which we get is basically a list of packets, or a stream of packets, and we have to arrange those packets into video frames, and that's basically what the parser does, and that's pretty much usual in the video streaming. Then we have to decode the video or decompress it, in other words, because it needs to be compressed in order to be streamed, otherwise it would require gigabytes of bandwidth. And then the video is still not ready to be processed by our neural network because it's in the YUV format. So like usually we have pictures in RGB format, so we can represent them as a union of those three layers. However, in video streaming, we usually have that kind of three layers, and we have like luminance or the brightness and two chromatic layers, because that's better for the video compression. So we have to convert that to RGB. And then once we have done this, when we are ready to detect the hand movement, so detect whether the user is moving, and we are going to use pre-trained yellow model for that. And when we have this detected, then we can generate the sound, and we're only going to generate those sounds when the user is actually hitting the drum. And WebRTC expects us to continuously receive the stream, or continuously send the stream. So we have to send the silence whenever we don't send any other sounds. Finally, we have to encode the audio, so compress it, and send over the network also via WebRTC. So let's get to it. I prepared a live notebook for doing that, and it's actually hosted on our server that is located in Helsinki, Finland. And we're going to check out how this is going to work. And I'm going to write some Elixir. I hope you see everything and understand as well. But it's not crucial to understand every character here. It's more about the concepts. So we're going to use membrane for the streaming part. So here are the steps that we need to do. And kind of membrane API is a pipeline based, so we can have those steps and use the pipeline API to express them in the framework terms. So first we're going to start a pipeline. Cool, we have that, and then we're going to tell it to perform some actions. So here we pass the specification of what should actually be in the pipeline, and we are going to use the child function to spawn like the components within the pipeline. Like these children can also like have children, so it's like parents-children relationship, so hence the name. So first component we are going to plug is the membrane WebRTC source. And we're going to tell it that it should establish the connection via WebSocket. So like the signaling or connection establishment will go through WebSocket, but all other things, so the media actually, will go through a custom WebRTC connection anyways. I'm going to tell that it's here. And I'm going also to tell it that the video codec is H.264 because we're going to decode it then. So then I'm going to tell it that I'm going to only take the video from there. So I need to pass the on option here. And then we basically have the video that needs to be parsed. So we are going to use H.264 parser for that, and then decode it with the FFmpeg-based decoder. And the last thing for now is to convert the pixel format of this, so there is YUV to RGB. And we are also going to use for some reason, I don't know, I don't have like auto-completion. So let's hope I remember that correctly.
I think you're not on the right module.
Let's try it for now. We'll think later. And finally, I'm going to, for now, use the debug sync. And to inspect what kind of stream actually we have and to verify that it's correct. So for that, I need to pass a kind of a handler here and tell it to inspect what we get. Okay. Oh, I forgot to bring in the import. Oh, maybe it's like this. Okay. And we received some video. I already have like the front-end part working here and trying to connect to my server. So that's why we got the video. Oh, let's get back. And we see that it has some dimensions and the pixel format is RGB. So we're fine with it. Let me terminate this for now. Okay, and like now the next thing is to actually detect the hand movement. And I just found a model pre-trained on GitHub, and I just borrowed it for the sake of this presentation. And so we are going to use eVision, OpenCV bindings to Elixir to like perform the inference. There are many ways to like infer on a neural network in Elixir, but that's the one I managed to like get working. So I'm not going to dig into this very deep because we don't have time basically. However, we just load the model and then we put the image and get the position of the hand on this image. And we need a bit of boilerplate and conversion there and back to prepare the image to be in the proper format for the neural network. And I also have, like in 10 lines of code, a detector of doing BAM. So basically, if a hand was up and now it's down, then it means there's a BAM. Also we have a BAM sound module, and it has two functions, format and BAM. So the BAM is actually the PCM PCM audio stream that we're going to send, and the format is like the parameters of this audio for the further elements to know. And here is our actual element that we are going to implement. So it basically says that it has one input and one output. It accepts video and sends audio that is uncompressed. And then we need to implement some callbacks. So this thing is called upon initialization, and each callback returns basically a two-element tuple, actions and the state. So actions are the commands for the framework, what it should do, and the state is like the new state of the element. So we're going to implement some callback. The first one will be handle stream format. So we already seen the stream format, but here we just get it, and we're going to save in our state because we're going to need the dimensions of the video. So we're going to input format, save that in the state. And also, we're going to produce some actions. So we're going to tell the further element what it should expect from us. So stream format, we're going to send it to the output. And we have it already here in the BAM sound. That format. And we return actions and the state. Cool. And actually now we can do our main work because we defined handle buffer callback. And here we basically get each frame of the video. And so what we are going to do is to perform the inference. So we are calling infer BAM detector. And the image will be the payload of the buffer. And the format is going to be the one we stored in the state. And also we have a model in the state. We just loaded it here. Whoa. And once we have the inference, we can use BAM detector .detect to tell us whether there is a BAM or no BAM. So inference and state, detector state. So here we have it, and then we can check whether there is a BAM or not.
You have a typo in inference in this line.
Where? Oh, inference. Thank you. And if BAM do, and then if we have actually a BAM, we are going to first write BAM. And then we're going to also send the BAM to the output. So buffer, output. Our buffer will be a membrane buffer struct with payload of state.bam because we loaded it here. So we're going to send it here and return the state. Otherwise, we're going to do nothing. And we also should update the detector state. Cool. And that would already work, I hope. However, there is one problem because the inference here takes some time, and we basically cannot do that on each frame. So what we are going to do is to try to make it asynchronous, and with Elixir it's actually quite easy. we can use a task module and pass it a function. And now it's already asynchronous. The problem is that we don't have the result here yet. So we're going to send it back. And we're going to grab the reference to the element with the self function. And we are only going to do that if we are not processing now. Because otherwise we would start this task for each buffer anyways. So we're going to start it only when we are ready to process the next frame. So now we are going to receive this inference in another callback, handle info. And we are going to move that logic from here to there. And here we're going to say that we are processing. And here we are going to say that we are no longer processing. Okay. Of course, I messed up something.
You don't have assign just point user in this line.
Thanks. Thanks. It's great that you are following. And yeah, we have our element defined. We don't know if it works yet, but let's hope so. It's 30% it works, I'd say. Let's try to plug it into our pipeline. So I'll make this a filter, so I can plug more elements here. And I'll plug bam bam. And then I'm going to use a utility element that will generate the silence whenever there is no bam. And an encoder that will compress the audio so that it can be sent via WebRTC. And then I'm going to plug another WebRTC element, sync this time. And it doesn't send any video. And I will change the port. And that's basically it. So here I'm trying to run this again. Something has failed, actually. Which one? No, we changed it half a year ago. So let me try again. That's the error I see for the first time. So it's actually pretty weird. But okay, I know what I missed. I just need to tell it that it's going to produce audio. Okay. Yeah, actually. Oh. Okay, so I finally received our video, and now let's check if the bumming works. So I try to wave my hand in front of this, and after some effort, I made it working, and I think I don't have time any longer, so I just very quickly summarize this. So we learned how to stream the media to our backend. We learned how to do the inference with it, and it's actually not that hard. And it opens up quite some possibilities before us. And the last thing I'd like to show is that we organize a media streaming conference here in Krakow in September, and it's going to be like awesome. It's the second edition. It's one of a few conferences like this in Europe. So you're very welcome to visit RTC on Live and check the details. And thank you very much for listening.
Do one more BAM. Oh, come on. Oh, no, I ruined it. All right, thanks.